Hi Rocio. So you had a question for me about why all the different normal distributions out there, and let's give a few examples of those, some concrete examples, uh, why they all in some way, how they all in some way relate to the standardized normal distribution. So let's just start by representing the standardized normal distribution. It's a bell-shaped curve. Oh, it's supposed to be symmetrical. Let's just give that another go. It's symmetrical. It has a. I'm going to get there in the end, Rocio. It's symmetrical, it has a mean of 0 and a standard deviation of 1. And actually, one thing I like to mention as well is it actually has a point of inflection, a non-stationary point of inflection, one standard deviation away from the mean. And it has an area, crucially an area underneath of 1. It does not pass through the y-axis at 1 or anything like that, and it has an extremely complicated equation, which I will show you in a moment. Now, let's call this the z-axis as well, because this is the standard normal. So we could say z is normally distributed with a mean of 0 and a standard deviation of 1. And these are z values, if you like. But really, they stand for the number of standard deviations you are away from the mean. Well, that is a standard normal, and that is the one, by the way. I know you printed out a copy of the tables or a screenshot of the tables. That is the only one the tables refer to, the standard normal. The tables will help you, obviously, once you've done the standardization step with solving any other problem you like, but the tables only actually give you probabilities or areas, if you like, for this standard normal, where the mean is 0 and the standard deviation is 1. Okay, now let's take another, something else which is taken to be normally distributed, something which I strongly disagree with and also think it's a waste of time, IQ. Uh, IQ was always taken to be normally distributed, and the mean is supposed to be 100, and the standard deviation is supposed to be 15. Yeah, and so if we're going from here to here on my graph, that would that would transform, if you like, to something like that. And I'll write down, let IQ be represented by x, be represented by the random variable x. Then x is normally distributed with a mean of 100 and a standard deviation of 15. But as you know, this is actually the variance, so I'm going to have to write 15 squared there. But it's much nicer, I think, anyway, to talk about the standard deviation, especially because of what the standardization step involves. We don't use the variance for that. We use the standard deviation. We just, it's just one of those, like notational well, a notational, it's just for notation's sake that we have the variance there, but it's never really made much sense to me why you'd want to put the variance there. I'd always rather the standard deviation was there. It's one of those things you just have to remember. Okay, so why do we only deal with the standard normal? Well, because otherwise every single different normal distribution would have different values, different probabilities, and there's no way we could actually record all of those values. But it's very easy to relate any other normal distribution to the standard normal distribution using the standardization step. And the standardization step is simply letting z equal x minus mu over standard deviation. That is the standardization formula. Now, if you look at it, when I look at this formula, what do I see? Really, I just see a function transformation. That's all it is. It is a linear function transformation. It's two transformations, actually. The minus mu just represents a translation to the right by mu, and the divide by sigma is a squash, basically, or stretch, if you like, in the x direction. Yeah, it'll actually be a stretch by a value of sigma. Let's just have a look at these two examples. Yeah, if you wanted to work out like the probability that x was less than 85 here, and you were using the old approach where we don't just type into our calculator, because I know the calculators do it all for you now, but the old approach was to use tables and do this. You replaced x with z, but you replaced, because 85 is your x value in question, you did 85 minus the mean and then divided by the standard deviation. Yeah? Now, what does that give you? It gives you the probability that z is less than minus 1. Because for both these problems, what we're really saying is the probability that somebody has an IQ under 85 is exactly the same probability that you are less than, well, under one standard deviation below the mean. It's exactly the same thing because all this really does, this formula here, which is a magical formula, is it is a function transformation which relates any normal distribution to the standard normal distribution. That's what that does, that formula. It's ever such a clever formula. Let me give you an example, yeah? Here is a curve, and it's actually y equals 1 over 1 plus x squared. And the reason I use that is because, as you can see, it kind of looks like the normal distribution. So I thought, this will be a handy one to do. It's not the normal distribution. Don't get too excited. I'll quickly show you you want to know what the equation is for the normal distribution. You'll see why we don't show you it at A level. One second, where's my file which I wanted to show you? Okay, the actual equation for the normal distribution is, oh, let me go back there, I'm messing that up, is this one here. Can I move it about? Damn it, I was kind of hoping I'd be able to move this about. One second, let me try again. Here we go. So this one here, look at it. It looks beastly. It really does. 1 over sigma times the root of 2 pi times by e to the power of minus a half x minus mu over sigma all squared. Yeah, that is the equation for the normal distribution, and that's actually not the standard normal. That will be any normal distribution where mu is, well, for example, for IQ, mu would be 100 there, and sigma would be 15. So yeah, it's a beastly looking equation, so it's a bit easier for me to just use this equation, which looks a bit similar. The only trouble is, as you can see, it definitely hasn't got an area of 1 there. It looks much more like it's got an area of like maybe 2 or something like that. I might even work that out. It's one of those integrals I really should know. But yeah, okay, so, well, let's say this is our normal distribution. Now, what I've done is I've decided to introduce an equation here, which is just like y equals 1 over 1 plus x squared, but I've called it 1 over 1 plus x minus m, which is like my mu, divided by a. A is going to be my sigma. I thought it was the closest letter to sigma, all squared. Yeah, and I just want to show you how that changes the graph as I vary mu and sigma. Well, it's just a function transformation. If I change mu, it just moves it to the right or to the left, yeah, and I'm doing x minus mu. So if I'm doing x minus 100, suddenly my curve is exactly symmetrical around 100. Yeah, it just moves it to the 100 to the right. Now, what about the divide by sigma? Well, this is a little bit less clear, but all that does is actually stretch it or squash it. So if I change a, oh, sorry, I didn't mean to do that. If I change A and vary it, look at that. As I make A bigger, A normally starts on 1 on the curve, doesn't it? Yeah. If I make sigma bigger, I actually end up stretching it out, to the left and right. Whereas if I make A smaller, and actually, strictly speaking, A can't be negative here. I should have changed the properties on the slider. But as you make A smaller and smaller and smaller, you squash it, yeah, until you've made it flat. But, it doesn't make any sense to talk about a standard deviation of 0. It means that your data set is all the same number. There's no variation at all. So yeah, as sigma gets larger and larger and larger, that just stretches out the curve. Now you might think, Mr. Nichols, though, Mr. Nichols, hang on a second. If it stretches the curve, as you can see here, that's going to distort the area and mean the area is over 1. If you were thinking that, brilliant, by the way, I think that's fantastic and bravo. Well, the reason it doesn't do that, if I can take you back to this ridiculously complicated looking equation here, if you notice, as you vary sigma, oh sorry, I'm pointing at the screen with my finger. You can't see my finger. Note to self, do not, that doesn't help. I'll use a pointer. Okay, so as you change sigma here, you are going to stretch it in the x direction, and that will distort the area, make it larger. But it's all compensated for by doing 1 over sigma here. And once you've got to the point where you can integrate this function at university, they will make you integrate it and prove that it always evaluates to 1. So don't worry, even though you're distorting the area in the x direction, you're also going to distort it in the y. Essentially, they would change on my example here, that would change the y coordinate as well, so that the area is kept constant at 1. So yeah, the best way to look at why the standard normal has all the answers for every other normal distribution is quite simply that every other normal distribution is just a linear transformation away to being converted to the standard normal. So that when we get a question like, find the probability that somebody's IQ is more than 85 or less than 85 or whatever, you would just do the value minus the mean divided by the standard deviation, and yet then you've converted it back to the standard normal. Geometrically, you've just conducted a stretch and a translation, and you've turned it into the standard normal distribution, and then it will have exactly the same answers for how, for the probabilities and the areas and everything else. Okay, I hope that was useful. I'm really pleased you didn't ask me to try and derive the normal distribution for you. I did actually have a little sneaky look online at some of the ways there are of doing that, and I'm tempted to make another video now to try and show you where this hellish looking equation comes from. I will actually just do the standard normal if I can just write down what it looks like, because it is definitely very interesting, and I mean, just look at it, it's just got so much fun to it. For the standard normal, it becomes somewhat simpler. F of x will simply be 1 over root 2 pi e to the minus a half multiplied by x squared, and I think that's it. Let me just check with my equation up here. Yeah, because mu's just going to be 0 and sigma's just going to be 1. So I think that's all right. Yeah. And that is the equation of the standard normal. Now, deriving that, that's much more of a challenge. Essentially, they came up with a normal distribution, I believe, by looking at things like the binomial distribution and taking the case where p is a half and n is very large. Well, when p is a half and n is very large, or as n tends to infinity, the limit of that should basically create this curve. I'm glossing over lots and lots of ideas, and I definitely haven't expressed it as clearly as I could have. But yeah, maybe that's for another video. Okay, I hope that helped, Rocio. Let me know if it didn't, or if there's anything else you want me to explain, and I'll have a go. Okay, bye bye.